MCube data. So why Moscoviense and Siokowski? Well, frankly, they're two of the most interesting places on the moon. Moscoviense has been shown with the near-infrared data that's been recently collected to be compositionally very interesting. And Siokowski, as I'll try to make the point in this talk, is one of the most interesting sites thermophysically. But starting with the compositional side of Moscoviense, we're primarily using the Diviner Lunar Radiometer data set here. Diviner has 3 channels in the mid-infrared near 8 microns that were designed to map the Christiansen feature of silicates on the moon. And the plots I'm showing here are measurements in simulated lunar environment in laboratories of Apollo soils. The left are new measurements that we made in about the last year or so at University of Oxford. And on the right are some of the measurements from the early 1970s in literature. So this was a very useful data set with a lot of foresight. So Diviner was designed to characterize this feature, and this feature shifts in a diagnostic way to shorter wavelengths for more feldspathic compositions and to longer wavelengths for more mafic compositions. So taking a look at Moscoviense, I'm sure most of you are very familiar with it. Large multi-ring basin that's been infilled in the center with mare. This is from Elrock WAC mosaic. And we can color it with Diviner, and we see the interior, more mafic materials are distinct from the exterior country rock, which is essentially anorthosite with a few fresh impact craters bringing up pure and more immature material. For Moscoviense, the margins, in the Diviner data at least, the margins between the mare and the floor impact melts are relatively fuzzy for impact craters, which is to be expected given its age. And Moscoviense has been highlighted in the last year or so for, on the western margin of the inner ring, some unique mineralogies that were observed by the M-cubed instrument. So these are figures from the Peters et al. 2011 paper showing their identifications of unique lithologies. These are relatively pure mafics. So there's olivine up here, and then there's orthopyroxene on the right side of this box, and in this box, and spinel in this box, and you can see in the integrated band, 1 micron band depth, that the spinel is really showing up quite strongly. When we look at these with Diviner, we're less sensitive to the actual mafic composition of those sites, but we are very sensitive to the feldspar to mafic ratio, and so we can say interesting things about how much country rock has been mixed into them. So for the olivine sites, which are this one and this one, the blue arrows, you can see that there's a great difference in the color of Diviner, even though these have fairly similar signatures with M cubed, and so we know that this site has quite a bit more feldspar mixed in with it. For the orthopyroxene, similarly, and unfortunately it's not really shown up very well on this projection, but this is the most pure pyroxene. This is kind of intermediate, and this is the least pure, and this even makes sense because you do have a small impact crater directly adjacent to the site, which probably had an influx of material. And then for spinel, they're a little bit more homogeneous. If we zoom back out and look at Moscoviense, in addition to the unique mineralogies on the western inner ring, M cubed and Kagoya data have been used to identify relatively pure olivine deposits in the northern portion of the basin as well as the southern portion. We've looked at many of these with Diviner data and identified some additional ones with Diviner data because we do have pretty good coverage of the Moscoviense basin. And to do some more, so what I was talking about before was pretty qualitative, but we can also do some more quantitative things with Diviner, especially when we use some of the near-infrared data sets as well. So we've been playing around with a concept study to do quantitative mineral mapping with Diviner and near-infrared data sets, and using multiband imager alone and using the techniques based on Lucy 2004 and Cahill et al. 2009. We looked at one of these olivine features, and using just the multiband imager alone, this feature looks more or less like pure olivine with almost no plagioclase, which is what has been reported. But when you start incorporating Diviner and our great sensitivity to the feldspar content, you see that this feature now appears to be relatively strong in olivine, certainly, but does have a lot of plagioclase as well. And even perhaps more interestingly, is on the western margin of this feature, you have a region that has very low plagioclase, and it has high orthopyroxene. So this feature actually has olivine plagioclase mix on the east side, and on the west side has almost pure orthopyroxene. So this is kind of a sample of the type of quantitative mapping we want to do, and we're hoping to get some funding to be able to do this globally using the MCube dataset and the Diviner dataset, in addition to the multiband imager. So if we move south to Siokowski Crater, you can see it's a large impact crater with a Mare infill, prominent central peak, and relatively steep sides, steep slopes on the sides. In this case, the Mare is very distinct from the melt country rock on the inner crater floor, and the central peak has strong plagioclase features that have been identified using MCube data, and they've also identified some pyroxene. So this is another good example for us to do some of our quantitative mineral mapping test locations. And then the inner part, sorry, not the inner part, but both the inner and the outer part of the crater rim, including the ejecta, have exposures of stronger plagioclase signatures. If we flip over to the other side of Diviner, and for some reason the map on the left isn't working, but it was intended to show the daytime time of day coverage as the surface warms up and then cools down. And then the plot on the right is showing the nighttime. So we start at the beginning of the animation with very warm temperatures, and things get colder as night goes on. The soil gets bluer over the course of the night because it cools off more. The rocks, the blocky material, stay warmer, and then we can use the temperature difference between the blocky materials and the soil materials to come up with an abundance for what the fraction of blocky materials must be. And that's what's been done here. This is work by Josh Banfield, and he recently wrote a paper, 2011, describing the methodology. This is showing the rock abundance for Tsiolkovskiy Crater. Highest rock abundances are in the central peak region and along the inner margin of the crater rim, but unlike many other craters that we see of Tsiolkovskiy's age, this is upper Imbrium age, we see significant blocky components in the ejecta, and basically haven't seen this anywhere else. So if we compare it to Moscoviense, which is a few hundred million years older, but a different formation process, there's just no comparison. Siokowski has far more blocky material. So maybe a better comparison is something like Humboldt, which is actually a little younger than Siokowski, and similar size, similar depth, and you still don't really have a comparison. Siokowski has far more blocky material than Humboldt, and for Humboldt, most of the blocky material is limited to the floor fractures. So this is a material that's being regenerated over time. This is El Rock Weck. The other thing we can say about the two craters is for Humboldt, the rock abundance is almost exclusively limited to areas that have low soil maturity, whereas for Tsiolkovskiy, areas that have low maturity are more likely to have rocks. But there are areas, and if you keep an eye on like areas like this and like this out in the ejecta, which have very high block abundances. Greater than 5% is something we rarely see on the moon. But when you flip over to the soil maturity, there's no maturity. So this is a mature area that has blocks, and it's something we're still trying to figure out what that means. So if we take a more zoomed out global view of what's going on here, you can see how rare Tsiolkovskiy really is. When you look at the Diviner rock abundance map, all of the points that have the highest rock abundance correlate to very fresh impact craters, Tycho, Aristarchus. Even Copernicus, doesn't have that strong of a blocky signature. Now, interestingly, there is one other feature that doesn't have an impact crater and has large amounts of block material, and that's the antipodal ejecta from Tycho. So it would be very convenient, very handy to say, well, perhaps this is antipodal ejecta from Aristarchus, but there are issues with that. For one thing, Aristarchus is far, far smaller than Tycho, and we're actually seeing more material at Siokowski. So that's probably not the lone hypothesis if it even works at all. But you can keep thinking and try to come up with some others. Well, Siokowski has been believed to have very thick impact melt deposits. But then you need to come up with a mechanism for what's exposing the blocking material. Siokowski is steep, but it's not uniquely steep. And so you it's hard to come up with that mechanism for solely explaining the blocking material, and that doesn't explain the blocking material we see in the ejecta, where the slopes are minimal. An idea that David Page has suggested might be extremely interesting, if we can find a way to prove it, is what if this is evidence for an iron metal impactor, a very large nickel iron meteorite impacting the surface. This would have a similar effect as blocky. You could actually have a lot less material if it was metallic iron and keep those warm temperatures overnight. But what's the mechanism for actually concentrating the iron metal? You'd expect that all the iron metal in the impactor would be vaporized, and then it would be hard to get it to form coherent structures. And the other hypothesis we're looking at is, what if it's incorrectly dated? Siokowski would look right if it were something more on the order of 1 to 2 billion years old, as opposed to 3.2 to 3.4 billion years old. But we don't really have any reason to question existing crater counts. So these are the mechanisms we're evaluating at the current time, and we'll have a lot more to say about this at EPSC once we start incorporating some of the other LRO and the newer data sets. But we're coming to the conclusion that it probably isn't going to be a simple single explanation. It's probably going to require several different mechanisms, such as perhaps the Aristarchus ejecta did come there, but it was the influx of Aristarchus material that actually exploited some of the instabilities and caused landslides or something like that. Or Matt Siegler had an idea, which should definitely need to be investigated, as to whether or not the secondary impacts from Aristarchus could have contaminated the crater counts, and perhaps it actually is younger, but then that has problems for how you get that much mare in a crater that size later in their history. Or some other ideas. So if you have a suggestion here, we're certainly willing to look at any ideas at this point. So in conclusion, the moon is a strange and fascinating place. I hope I get to put that in every conclusion slide I have. Moscoviense is compositionally unique. I think this is a great place to bring back samples from. If you have a rover, you could collect almost all the end members we see in the lunar remote sensing. It's also a really good test site for understanding the Diviner feldspar-mafic ratio. And Siokowski Crater is definitely thermophysically unique. And it is also compositionally interesting. And I think no matter which formation mechanism we ultimately favor, it's still going to be a compelling case for future exploration. And the final point is that the Diviner data set in PDS, which is actually what was used here to see that Tsiolkovskiy looked different, has the potential for discovery. So don't feel like just because it is in PDS, it's already been gone through completely. That's definitely not the case. And we encourage anybody who wants to look at Diviner data to look at it. And if you have questions, ask a member of the team. Thank you.
Mark first. Why did you put on that bullet and back up? No reason to question existing crater counts. That's patently ridiculous.
Well,
you should question every crater count.
The crater counts of the Maria, were solid. They haven't been looked at in a long time. But
I'm not a crater count expert and all that, but there's people who are working on LROC data who go back and redo old crater counts, and not in a single case have we reproduced previous crater counts. Like, for instance, Copernicus, which is, how important is Copernicus in lunar chronology? Right? When we went back and counted those, Copernicus is no longer an anomaly. It fits right on that, the Neuquén curve, right, whereas it fell off before. People have been going back and recounting Mare crater counts. The whole idea that Imbrium has units that are between 2 billion and 3.6 billion can't reproduce that. So you should question the crater counts.
Well, and I'm very excited to have members of the LROC team interested in this and willing to provide some expertise in that area. And students.
Quick question, Marlon. And then we'll have to cut it off.
But while you have this up, I'm fascinated by your antipodal work, especially with Tsiolkovskiy. And it seems to me, well, go back. you can add one more column on this, because the antipodal data suggests there are blocking material there. And maybe looking at some of that data will help clarify that. Yeah. But if the Siokowski area is inherently geologically more blocky, it's got more coherent material, that would be consistent with your antipodal data and certainly merits detailed investigation. That's very exciting.
Yeah, and we've looked at this somewhat with the Tycho antipode, and with the Diviner data, we see blocking material that's kind of offset from the melt ponds that LROC sees, and it's interesting, complex story. No crater, no.